We often say that pi is approximately 3.14. Sometimes we go further. 3.145, 3.1 These numbers clearly get closer and closer to pi. But here's a surprising question. Are these actually good approximations? For example, 3.149 is really 3.1 divided by 1,000. That's a very large denominator for a very modest improvement. Meanwhile, fractions like 22/7 or 355/113 are astonishingly accurate despite having very small denominators. So today's question is this: how do we systematically find these best rational approximations of irrational numbers like pi? To answer this, let's stop thinking about decimals and start thinking geometrically. Imagine a rectangle. Its width is pi, its height is 1. Now ask a simple question. How many unit squares with side length 1 can we fit inside this rectangle? Since pi is a little more than 3, we can fit exactly 3 squares. After removing them, we are left with a smaller rectangle. Its width is pi minus 3. Its height is still 1. Now rotate your perspective. Think of this remaining rectangle as having width 1 and height pi minus 3. Again, ask the same question. How many squares of size pi minus 3 can we fit inside? The answer is 7. So we remove 7 squares, and again, a smaller rectangle remains. And now we repeat the same process over and over. This simple cutting procedure is not random. It is exactly the same process used to build a continued fraction. In fact, what we have just done geometrically corresponds to the expansion pi equals 3 plus 1 over 7 plus 1 over 15 plus 1, and so on. This is the continued fraction of pi. Now here is the key point. If we stop this process at any stage and turn the partial continued fraction into a rational number, we get something remarkable. We get fractions like 322/7, 355/113. These are called convergents, and convergents have a powerful property. Each one is a best approximation. That means, among all fractions with denominator no larger, none comes closer to pi. This explains something important. Decimal approximations approach pi slowly and inefficiently, but continued fractions organize approximation optimally. They balance accuracy and simplicity. This is why 22/7 and 355/113 have survived for centuries. They are not lucky guesses, they are forced by structure. And this idea goes far beyond pi. Every irrational number has its own continued fraction, and every one of them produces its own sequence of best approximations. All of this begins with a very simple idea: cutting a rectangle into squares. Sometimes the most powerful mathematics starts with the most ordinary pictures. In the previous part, we saw something surprising. Fractions like 22/7 and 355/113 approximate pi incredibly well. And they are not lucky guesses. They come from continued fractions. But this raises a deeper question. Why do continued fractions produce the best possible approximations? Why are they optimal? To answer this, let's change how we look at the problem. Forget numbers for a moment. Think in terms of geometry. Imagine a coordinate plane. Now draw a straight line starting at the origin with a slope equal to pi. This line represents the irrational number pi. Next, look at all the lattice points on the plane. Points with integer coordinates. Each lattice point corresponds to a fraction. The vertical coordinate over the horizontal coordinate. So approximating pi by fractions is the same as asking which lattice points come closest to this line. Now here is the key idea. Most lattice points are not interesting. They are either too far from the line or they require very large coordinates. What we want are special points. Points that get very close to the line without using large numbers. These are the best approximations. And here's the remarkable fact. The lattice points corresponding to continued fraction convergence are exactly those points. They lie alternately just above and just below the line. And they do something very important. They block everything else. Once a convergent appears, no other lattice point with a smaller or equal denominator can get closer to the line. This is what optimal means. Continued fractions do not skip good approximations. They find everyone in the correct order. Now let's compare this with decimal approximations. Decimals move horizontally in fixed steps. 10, 100, 1000. They force the denominator to grow rapidly whether or not accuracy truly improves. In geometric terms, they jump blindly across the plane. Continued fractions behave differently. They move only when necessary. Each step is a greedy choice. Subtract the largest integer possible, then invert what remains. Geometrically, this means The algorithm always looks for the next lattice point that comes closest to the line without crossing a better one. This is why convergents are not just good approximations. They are unavoidable. If you try to find a better fraction with a smaller denominator, you will fail. The geometry forbids it. This is also why continued fractions appear everywhere. In Diophantine approximation, in dynamical systems, in the theory of algorithms, they capture the most efficient way to approximate irrational numbers. So when you see a fraction like 22/7, you are not seeing a trick. You are seeing a geometric necessity. Continued fractions are optimal because they follow the geometry of the number itself. They reveal the structure one best step at a time. In the last video, we looked at a geometric picture, an irrational number represented as a straight line, and lattice points approximating that line as closely as possible. Continued fractions appeared naturally as the optimal way to find those lattice points. Now comes the surprising part. This picture is not static. It hides a dynamical system. This connection is known as the Dani correspondence. To see it, let's slightly change our perspective. Instead of fixing the line and searching for lattice points, let's fix the lattice and move the space. Think of the integer lattice as a grid in the plane. Now imagine applying a continuous deformation to the plane, stretching in one direction and squeezing in another. As time passes, the grid changes shape. Some lattice points move closer to the line, others move farther away. This stretching and squeezing is not arbitrary. It is controlled by a diagonal flow. Geometrically, this flow tries to align the lattice with the direction of the line. And here's the key idea. Good rational approximations appear exactly when the deformed lattice comes close to having a very short vector. In other words, approximating an irrational number is equivalent to asking, does this moving lattice come close to the origin? This is the Dani correspondence. It translates a number-theoretic question about rational approximation into a dynamical question about trajectories in a space of lattices. Continued fraction convergence now have a new meaning. They correspond to special moments in time when the lattice is especially well aligned, moments when a short vector appears and then disappears again. From this point of view, continued fractions are no longer just an algorithm. They are a record of a dynamical orbit. This perspective is powerful. It allows us to use tools from dynamics to study number theory, recurrence, non-divergence, ergodicity. All of these concepts now say something precise about Diophantine approximation. So the story comes full circle. We started with decimals, we moved to fractions, then to geometry, and now geometry has turned into motion. The Dani correspondence shows us that approximation is not just about closeness. It is about how structures evolve over time. And once you see that, you realize something deeper. Numbers are not static objects. They live inside dynamical systems.